invitation to this workshop. I was only able to arrive yesterday, but already in the day and a half I've been here, I feel that I've learned a lot of interesting things. I'm going to be talking about generalizing G-equivariantization, and mainly what I have in mind by that is um, generalizing the gauging of what are called invertible symmetries in 2+1 dimensional topological orders to the non-invertible case. And I'll mention also other work by other people that has been done on this. I'm going to focus on one very, very specific aspect of the work that we've done to try to hopefully get some kind of input from mathematicians here or mathematical physicists here. Unfortunately, this talk is probably not going to be very mathematical, so we'll see if we find some common language. So I should say this is based on work with mostly junior collaborators, with the exception of Clément Delcamp. So maybe I'll just advertise them a little bit. So one of them is Mahesh Balasubramanian, who is a PhD student of mine at Queen Mary. He's applying for postdocs this year. Another one is Rajath Radhakrishnan, a former student who's now a postdoc at Oxford. And then we had a related paper, which I'm not going to talk so much about, which is more about quantum information theory and some entanglement bootstrap applications of this with Roman Geico, who's a postdoc at UCLA, Milo Moses, who's a PhD student at Caltech, and Bowen Shi, who is a postdoc at Urbana-Champaign. So these are the basic theories that I want to talk about. So maybe I'll try to define a little bit what I mean by topological order, because there can be various definitions. So up to some caveats that won't be relevant for this talk, by a 2+1D topological order, I'll basically mean some theory that corresponds to some unitary modular tensor category. And in this context, the objects in the unitary modular tensor category correspond to topological lines that have non-degenerate braiding and some non-trivial fusion. So because I'm going to have difficulty making very general statements, I'm going to have a lot of examples in this talk. And so just to get us on the same page, as an example of a UMTC, we can consider SU2 at level K Chern-Simons theory, which has K+1 simple lines with Dynkin label 0 up to K. Okay? And there are many other examples. So I'm going to come back to examples of discrete gauge theories later in this talk. So a canonical textbook example of these kinds of MTCs is the Z2 discrete gauge theory, for example, or the toric code topological order for the condensed matter theorists. So before discussing equivariantization, which has to do with gauging symmetries, let me just say a few words about what the symmetries are of these theories. So a not entirely satisfactory physical definition of symmetry, which is not general, but turns out to be sufficient for this class of theories, is that a symmetry corresponds to topological defects or operators. Okay, and I'm going to use these notation, the idea of defect and operator interchangeably, because I'm going to mainly be thinking about Euclidean space-time. And the symmetries, at least in this kind of classification of symmetries where you think about topological operators or defects, are called P-form symmetries. And in 2+1 dimensions, they're generated by topological defects of dimension 2 minus P. Yes?
What are the examples that fall beyond?
Yeah, great. So one example, so a very interesting set of examples would be in 2D CFT, let's say, where you can consider some lines. Let's say just take a topological line in 2D CFT and suppose that it has a holomorphic field living on it. So that happens. An example would be the Z2 line in Ising, right? It has a fermion living on it. And now if you imagine taking that, a line and perturbing by integrating relevant, let's say, holomorphic field along it, you get a symmetry. It commutes with the Hamiltonian, but it's definitely not topological, except in the infrared.
Okay. So you mean this maybe subsystem symmetries or something like that? Some more localized, maybe object.
Yeah, I mean, that could be an example. I mean, here, this is very similar to what people would call normal symmetries, except that it's just not topological. It commutes to the Hamiltonian. Yeah. Any other questions? So the P-form symmetries in 2+1 dimensions are generated by topological defects of dimension 2 minus P. So the usual symmetries that you might think about are zero form symmetries. So those are things that live on codimension 1 surfaces. But you can have higher codimension, right? I mean, this is maybe probably not surprising. And at least in the HEP-TH world, the paper that sort of drove this point home was the generalized symmetries paper of Gaiotto, Kapustin, Seiberg, and Willett. And because there are these sort of larger class of symmetries, we can ask in Chern-Simons theory, for example, or in the topological orders, the more general topological orders, we're going to study what are the corresponding symmetries. And for example, in SU2 at level K Chern-Simons theory, since the Wilson lines are topological, you can think of these as corresponding to one-form symmetries. And these symmetries can be invertible if they satisfy fusion rules corresponding to a group, or non-invertible if they don't. So my definition of one-form symmetry is going to be a little bit different from these guys because they talk explicitly about invertible one-form symmetry, but I'm going to call any p-form symmetry a symmetry that has a charge of dimension p that's topological, and I don't care whether it's invertible or not. So just to drive this point home about invertible versus not, let's consider again SU2 at level K Chern-Simons theory. So there, the Dynkin label K line turns out to be invertible because if you take the Dynkin label K line and fuse it with itself, you get the trivial line. So this is the center symmetry of the SU2 Chern-Simons theory. And this corresponds to a Z2 one-form symmetry, an invertible symmetry. But more generally, if you have level K greater than 1, the remaining lines with Dynkin labels from 1 to K minus 1 are non-invertible. And they're non-invertible in the sense that if you take the line times its orientation reversal, you get the trivial line plus a bunch of other stuff. And these ellipses will be non-trivial for this set of Dynkin labels. But and more generally, if I have some unitary modular tensor category B, the line satisfying L times L bar, where this is the dual, lines that have the identity, the trivial line. So here I've called it the identity line. Previously I called it 0 because I was using the Dynkin label, so apologies for that. But anything that includes non-trivial ellipses, non-trivial lines appearing in the ellipses is non-invertible. But in any case, all the lines, all the simple objects of the UMTCB are going to be one-form symmetries. And then, of course, you can ask, what are the other symmetries? What other symmetries are there? And other symmetries are going to be important when it comes to talking about G-equivariantization. So one other set of symmetries that we can have are topological surfaces. So these are S, these are codimension 1. And even though there are no point-like operators in the Chern-Simons theory, the surfaces can act on lines, right? They can act on lines in this way. A line could come in and pierce the surface S and a new line B could be transmitted. So here on the surface S, we have some topological junction between the line A and the line B. Okay. So in general, this will be a non-trivial action. And this action may or may not be invertible. So invertible actions will correspond to cases where given a particular A, there's a unique B that appears. But more generally, we'll see that there are lots of examples where given a line A, there can be lots of different lines B that appear. Maybe I won't write an example yet, but I'll just say that. So again, yeah, just to drive that point home, the zero-form symmetry surfaces can be invertible or non-invertible. So when they're invertible, they satisfy the fusion rules. The surfaces satisfy the fusion rules of some group. And when they're non-invertible, they satisfy some more complicated set of
just a very silly question because I'm from different fields.
Yeah, sure.
Why do you call them symmetries if they are not invertible? I mean, you surely have a reason.
Yeah, that's a great question. So there are a couple of reasons. One reason is that at least for physicists, if I compute correlation functions, say by inserting these surfaces, right, I can freely deform these surfaces. They're topological, so I can freely deform them basically without changing the correlation function. And the only time things change is when they cross, let's say, something that's charged under them. So in that sense, they're symmetries. Also,
Symmetries of the correlation function. So
I would say then therefore symmetries of the theory.
So in which sense are they non-invertible then?
Yeah. So for example, I mean, we'll have a little example maybe in the case of toric code. So in the case of toric code, this is a sort of a simple MTC with the following simple objects. These are some bosons. These two things are bosons. These are fermions. And it'll turn out that we can construct a surface from the electric lines, surface that's E, which satisfies the following kind of fusion rules. SE times SE equals 2 times SE. So this I would call non-invertible. Well, there's no surface. SE is the same as its orientation reversal. There's no surface when you sort of multiply these two surfaces together, you get just the trivial surface. So in this sense, it's not invertible. And its action on,
Just to be invertible with respect to this fusion.
yeah, both with respect to the fusion and also with respect to the action on lines. So for example, when I send a line E into SE, I can get two possibilities. One possibility is E comes out, but I can also have a junction between E and SE where the trivial line comes out. So in this sense, it's also non-invertible. It doesn't.
Invertible just means that the DHR endomorphism is invertible.
That's actually surprisingly helpful. Thank you.
Did not know that. I'll make a note.
Thank you.
The sociological comment, that kind of 1980s. I don't know. I don't know why it's like 2000.
But most of these can't be realized as deep learning. These are more general. than
Yeah,
deep
yeah.
learning.
Yeah, sure, it's stuff with higher dimension.
Okay.
That opened my eyes, Stefan. Okay, thank you.
Okay, so these surfaces can be constructed by it turns out by inserting a mesh of non-trivial lines in B. So at least for topological theory, the surfaces are determined in some sense by the lines. So in this case of SE, we can essentially take basically a sum. We can take the simple object, the trivial line, and the E line, and we can sort of in some way that I can't draw very nicely, sort of draw a network of lines, topological lines, and form the surface from that. And when we take all sort of separable symmetric Frobenius algebras that we can use, so with a multiplication structure defines a separable special symmetric Frobenius algebra, you can use that to sort of build surfaces by using that algebra and creating a mesh that you insert on some codimension one slice of space-time, and this builds up the surfaces from a mesh of lines. So this, yeah.
There's this two category structure. Isn't that a condition that in order that the surfaces have the structure of a braided of a
So the surfaces, the braiding itself is the braiding of lines, right?
So you automatically get a two category, or is that
Yeah.
another
You ought to,
condition on the
so
lines that you start with?
right. So if I start from some modular tensor category B, I automatically get these surfaces for free in the physics literature by doing what's called higher gauging, in the math literature basically by inserting a network, an algebra object built from those lines. Of course, not all sort of naive objects that I could insert here work because they need to have a vanishing anomaly. Basically, they need to have a trivial, some
So
kind
there
of,
is a condition.
there is a condition, but all possible surfaces I can construct here come from these kinds of networks, if that makes sense. Okay. In fact, yeah, in the toric code example, basically anything goes because the associator for toric code is trivial. Okay, so when these surfaces are invertible, so again, if I don't know if toric code is meaningful to people here, but if it is, we can construct an invertible surface in the case of toric code by taking the fermion and sort of inserting a mesh of 1 plus f. And this generates a surface, which is called SEM, the EM duality surface. And this is an invertible surface, an example of an invertible surface. It's a surface that exchanges ENM and keeps F and 1 the same. So this is invertible in the sense that I've described. Also, it generates, if I take a fusion of SEM with itself, I get the trivial surface. So it generates a Z2 that's pretty invertible. But more generally, even in the toric code, I'm going to have some non-invertible surfaces like SE and various others. But when I have invertible surfaces, their fusion is described by a group, and there's a well-known mathematical way to describe the resulting theories. These are called G-cross braided tensor categories. And as far as I understand, I might be wrong, but Turayev was the first mathematician to introduce it. And then there's a very nice condensed matter paper by Barkeshli, Bonderson, Chong, and Wang that makes use of this construction and explains a lot of the physics. And the idea is that in these G-crossed categories, you can write a kind of grading, and I'll call that B sub G. And that grading is by the group elements in G. Okay? And the trivial component, B1, is the so-called untwisted sector. So that is the sector of lines that existed before you constructed these. In the case of toric code, B1 would just be the lines that existed in the 2 plus 1 dimensional bulk. Okay? But more generally, when you have some surface G, with non-trivial G, non-trivial group element, they will define twisted sector lines. And the twisted sector lines are basically lines that live as boundary conditions of some surfaces. So they're lines that are attached to surfaces. So in the case of SEM, I'm not drawing this very nicely, but I could imagine that they sort of the surface extends in these directions, but that there's a boundary condition here. And there are two boundary conditions that I can put, essentially Dirichlet and Neumann boundary conditions, which I can label as sigma plus minus, say. So these will be lines. These are non-genuine lines or twisted sector lines in the sense that they're attached to a non-trivial surface. And for more general groups, I get some more complicated story, but it's quite similar. So what's the relevant data that captures the G-crossed category? So one relevant piece of data is the permutations. So in other words, when I have an invertible surface, I send in a line, I get a unique line as output, and I can think of that, of course, as a permutation of the set of lines. That's one thing, simply the action of the surfaces on the lines.
Question?
Yeah, sure.
So in this general context or abstract, is there some way to determine what is simple or not? Or it's
Right.
by definition?
Yeah. I mean, so it's simple in the sense of, yeah. So for all intents and purposes, it's basically by definition.
Quantum field theory wouldn't be by definition. So I want to know if that's a difference between topological, I mean, this kind of topological discussions and in local quantum field theory. So there is an independent notion of what is irreducible, and I feel that a lot of kind of disagreements between it's just this kind of freedom that you have in the. Is that correct?
Well, so the simple lines, we can sort of define them as lines that can't be expressed as kind of a direct sum of other lines, and similarly for
Exactly, but sometimes then you define another theory by saying that that now a sum gets now you call it simple.
So
in
that
new
will
theory.
So that will happen actually. We'll see
Well,
that
exactly,
when you
but-
gauge.
but
For
then
example, when you gauge, a sum becomes simple in general.
Exactly, but you can do that. Okay, yeah.
But a gauging, I would say, gives you a different theory.
Yeah.
But in the case of this kind of gauging, there's an invertibility. If you think about things too categorically, there's a way to go back and forth. So it's not a violent change, but it's a different theory, I would say.
Yeah, good.
So another piece of data that you get is another piece of data that characterizes, in addition to the action of the surfaces on the lines, is the so-called symmetry fractionalization. So I should have drawn here, but you can imagine behind here a line A, where essentially this whole vertex, so I have two surfaces labeled by group elements G and H coming to another element GH, and I have a line new red that I've inserted at the junction. And this gives me a fractionalization in the sense that if I imagine sort of sitting behind this projector, another line, say A, I can imagine dragging this junction above or below that line, and that'll give me an action of the surface and the junction in particular on the line. And I can also think, I should have said, by the way, I should have driven this point home. In this BG, I'm really thinking about these elements here. I think I've said it, but I'm really thinking about these elements for non-trivial G as being sort of boundary conditions, right? This is defining some fusion 1 category of boundary conditions attached to surfaces in general. And then I'll have also a trivial surface, and I'll have bulk lines, but these will define some kind of fusion 1 category. So another piece of data that I have is the fractionalization, and this fractionalization determines the action of these. It comes from the action of these junctions on lines, and also this new GH. You can think of it as modifying the fusion rules for boundary conditions of the surface G and H to GH. So in particular, the particular line or lines that I choose to insert on this red junction will change the fusion rules for boundary conditions of lines at this trivalent junction. And this is specified by some class, it turns out, in H2G AAB, where AAB are abelian lines. For example, this line nu that I have here is an abelian line in the theory. So this is called the symmetry fractionalization, and it's another piece of cohomological data that defines the G symmetry action on the lines. Then there's yet another piece of data called the Postnikov class, which is an element of H3G AB. So G is the group G, the symmetry group G, and AAB are the abelian lines. And essentially what happens is if I make some kind of gauge transformation, or if you like an F transformation, this diagram is interpolating between two different configurations of defect that are linked to each other by an association, an application of an associator. What might happen is that at this junction here, a one-form symmetry line might appear. And that beta, in general, can be non-trivial. And if it's non-trivial, then what this means is that we have a two-group, essentially, a two-group that combines the zero-form symmetry of the surfaces and the one-form symmetry of the lines. And what that means is that when you try to gauge, say, a group, in this case, you're kind of doomed. You have to also add gauge fields, basically. For the one-form symmetry line, you have to actually gauge a full two-group. Okay? And finally, a final piece of cohomological data is the so-called Tuft anomaly. So this is something that lives in H4 GU1. And basically, it's a kind of, if you make sort of background gauge transformations, background G gauge transformations, it leads to some phases in the partition function, and it's an obstruction to being able to gauge the symmetry G. Okay, so these are the cohomological data that you have in the invertible case. You have some Tuft anomaly, which is valid in H4. You have some Postnikov class, which tells you whether you have a two group in H3, and you have some symmetry fractionalization H2, and some action rho surfaces.
I think I missed that. What is rho?
Oh, sorry. Rho is the action, is this because you can have in principle an action of G. Yeah, maybe didn't make it clear, but you can have an action of G, a non-trivial action of G on the lines.
Rho. So that defines a. So how does it define a cohomology?
Well, so you have to include the rho action in H3. There are also interesting cases where rho acts completely trivially. You can still have this. You can still have some you still have some non-trivial. You can have non-trivial fractionalization, which are basically related to group extensions, and you can have still some non-trivial Postnikov class.
So this is
Actually, Postnikov class is trivial in that case. Yes,
so this is group cohomology, and the action is determined.
that's right. Yeah. Okay, and basically performing so in this case, if this H4, if this omega is trivial in H4, and if beta is trivial in H3, then we can gauge G. Okay, and if beta is non-trivial, then we gauge it. We can gauge a two group.
What does it mean? Sorry, I'm asking all the
No, that's great. Yeah.
questions. What does it mean? I can gauge.
Oh yeah, so I'll get to gauging in a second. What it means intuitively is just you can sum over the surfaces. You can essentially insert an object corresponding to a sum of the surfaces and some multiplication, and you can insert it on the manifold and perform that sum.
Okay.
I'll say a few more words.
These are the cohomological abstractions to doing.
That's right. That's right. And they're completely classified. They're known completely mathematically, and they've been interpreted sort of physically, mostly by Barkashli and friends.
Good, thank you.
So yeah, I'm going to explain a little bit more what's meant by gauging. But even before we gauge, so the idea is we start from some theory, say toric code, which has some set of genuine lines, some set of bulk lines. We can construct surfaces from it. And then we can try to gauge a symmetry. But even before we do that, we have the ability sometimes to add a theory to sort of imagine tensoring in some sense, a theory that doesn't affect the content of genuine lines. So these are the SPTs, which I think made an appearance in the talk yesterday. And in particular, in 2+1 dimensions, we have the ability to add SPTs labeled by H3 GU1. So these are essentially just some a theory basically of surfaces and boundary conditions for surfaces, unique boundary conditions for surfaces, if you like. So they don't change the content of the genuine lines, but they add for you some additional degrees of freedom. So some additional non-genuine lines that are attached to G surfaces, and they can in general have a non-trivial associator that's characterized by H3. Okay, so you have this freedom in general to consider stacking with an SPT and then performing the gauging. And then performing G-equivariantization gives the gauged theory. So one question, your question essentially is how do we understand the gauging physically, and how does this generalize? So far the discussion has been just for invertible surfaces, and how does this generalize to non-invertible surfaces? So at one level, gauging is just a trivialization of the SG surfaces. So imagine that we have originally, we had the situation where we had this situation where SG was this non-trivial surface, and we imagine that some line A comes in and a line SG of A comes out, and there's some topological junction at that point there. And if we gauge, well, one thing that ought to happen is that we should be trivializing these surfaces. So in particular, if a line A and a line SG of A are related by the symmetry, then in the gauge theory, if there was a topological junction on the original surface, in the gauge theory, these should form some non-trivial object, right? Some non-trivial simple object. So this is kind of your question. So if here we have E and M that are, E goes in, essentially say M comes out. And now if I'm going to gauge this Z2 symmetry, turns out there's no anomaly, so I can gauge the symmetry, then I'm going to get an orbit from combining E and M. So that new thing, E plus M, becomes a simple line in this gauged theory, although it was non-simple in the original theory. So we get non-trivial orbits. And also, if I have any boundary conditions, let's say, for non-trivial surfaces, when I trivialize the surfaces, then the lines must become genuine lines of the gauged theory. So a little bit more precisely, we can think about gauging as inserting a sum of these surfaces. So we have a surface SG for each G, and we insert some kind of network, sort of some generalization, which I can't draw of this kind of network, but now in all of space-time. And we also have to insert, we also have to include an appropriate multiplication. And if you want to think one categorically, you can think about that multiplication as basically the multiplication in the fusion category BG, which I defined before. So BG was this category, this G cross category, which comes with some multiplication. And you can think about this multiplication as that one. Okay. So now what we want to do is we want to imagine inserting some sum of surfaces on the space-time manifold and essentially performing the sum in our correlation functions. And so if we go back and we consider now the action of the sum, so here I have a particular SG, but if I consider the action of a sum of SGs on this, in general, I'm going to get a line A, but I'm not just going to get A, but I'm going to get a direct sum of A sub pi, where pi are irreducible representations of the subgroup of the G symmetry that stabilizes the line A. So in particular, there'll sometimes be surfaces that leave the A lines invariant. And when I do that gauging, I get some sort of Ka dimensional vector space living there, and I can think of the line as some quantum mechanics with Ka symmetry. And so when I perform the gauging, I should get that vector space will break up into all the possible irreducible representations of Ka, and I'll get some non-simple line that appears. So as a special case, when A is the trivial line, which is stabilized by everything, I should get basically all the rep G lines. So this is the dual quantum symmetry that Vafa wrote about in his paper. Maybe it was known perhaps before then, I don't know. But yeah.
Question. So you had the sum over G.
Yeah, that's right.
So this means that you always think about discrete symmetry.
Yeah, I apologize. I should have said that this talk is about discrete.
Okay.
Yeah. It's
Is
an
there-
interesting question for. So there is some discussion. I don't think there's mathematically rigorous. I mean, in principle, although I'm not presenting it as such, this is mathematically rigorous. But I think for for Lie groups and stuff, the similar construction is not understood at the same level of mathematics.
But people are working on it, I assume.
Absolutely. So in particular, if you set A equal to 1, if A is the trivial line, then everything, as I said, the whole group stabilizes it. So this A line splits into lines, Wilson lines, basically, that are characterized by all the irreducible representations of rep G. And this forms some rep G, some dual one-form symmetry. So if you gauge a G0 form symmetry, then you get a rep G one-form symmetry. Okay, so superscript 0 and superscript 1 are the indicators of 0 form and 1 form symmetry. And in principle, you can also gauge the rep G 1 form symmetry, which means sort of taking this diagram I've written here and expanding it sort of in all of space-time. So I can imagine taking this slab and kind of thickening it, and then I'll get some network in all of space-time. That means gauging rep G, and I can go back to the original G symmetry. So one question is, how do we generalize all of this to the non-invertible case? Is this roughly clear? Maybe too hand-wavy, I don't know. But okay, so the proposal, and there's lots of other very relevant work, in particular by Liang Kong and collaborators, and also Corey and collaborators, Fiona and Houston and Pennies, have some work where they're essentially basically doing this. They're essentially doing some gauging, maybe in slightly different language, but it amounts to the same thing, gauging general symmetries of general zero form and one form, two group and generalizations of two group symmetries. So here, what I want to just highlight is roughly the proposal. So in this column here, I have the zero form, the invertible case, and all the cohomology that defines it. So here I have some sum on surfaces labeled by a group. Here I have, I want to generalize this, so I want to consider now maybe not just the sum on surfaces labeled by some group, but now I'm going to have some more general sum on surfaces. So these surfaces were invertible, but in general, I can also consider some sum on non-invertible surfaces, and we'll discuss this soon, and try to sort of sum over these and insert these on a space-time manifold. In the G-crossed case, there's a fusion 1 category of boundary conditions of these lines, E sub G. And in the generalized case, there will also be some fusion 1 category of boundary conditions for these non-invertible surfaces. Okay. And I should say that sometimes I'll perform in the discussion that follows, depending how much time there is, I don't know, I'll perform the sort of naughty thing of just sort of forgetting about the distinction between the object and the category, which is dangerous because, of course, the category is specified not just by an object, but by multiplication and all sorts of other data. But then there are also various other things that one can do. So there's a nice fixed point theorem for a group like for invertible symmetries. So you can ask a zeroth order question that you could ask about the G-cross cases. You know, how many non-genuine lines are there? How many basically boundary conditions do you have for invertible surfaces? And there's a sort of a fixed point theorem for modular tensor categories that essentially shows that the number of boundary conditions is determined basically by the number of fixed points of the action of the surface. So for example, in the EM case, the identity line is of course fixed because if a trivial line goes in, the trivial line comes out. Also, this fermion is fixed. So those are two fixed points, and there are two corresponding Dirichlet-Neumann boundary condition corresponding to this. And this is a general fact that you can prove. Similarly, you can, in our paper, we do it. I'm not going to discuss it here, but you can also prove a fixed point theorem for general non-invertible surfaces, where by fixed point, I just mean that you have a junction. So SE surface is an example. You have a junction where the E line can meet with itself, even though the E line can also meet with a vacuum. So then I would call E sort of a generalized fixed point. And of course, the identity is also a generalized fixed point. And then this surface here should have two boundary conditions. And we have some nice proof of that in this paper, but I won't describe it in more detail. Another thing that we have is we have symmetry fractionalization, which is given by this class, basically labeled by junctions of three symmetry defects meeting on a line. And then there should be some generalized notion of symmetry fractionalization. And basically that should correspond to some choice of fusion rules for this fusion category. Similarly, I mentioned there's a choice in the invertible case to stack with some SPT, some H3. And there should also be a choice in the more general case of choosing different associator for AS. Okay, that should be the generalization of discrete torsion. Similarly, there's a notion of an anomaly-free symmetry. That's a symmetry where both beta, remember that's H4G U1, the 't Hooft anomaly. Sorry, that's the Posnikov class, H3G AB with rho action. Where both beta and omega, the H4G1 vanish, that's a notion of some kind of anomaly freedom. And the more general statement, as I'll try to motivate over these next couple of slides, is that there exists a braided tensor functor from B to the Drinfeld center of this AS fusion category. This is not my work, of course. This is stuff that's been known for a long time. But one thing that I would like to ask, and I get to ask it, I guess, because the time's not up, but one thing that I'm interested in that we have so far absolutely not succeeded in is coming up with some kind of cohomological, or maybe I just had a brief discussion with Corey, maybe it's not the right way to phrase things, but some kind of algebraic or topological groups, or whatever you want to call them, associated with these more general these more general kinds of symmetries. Okay, so here we have a nice cohomological description in terms of H2, H3, H4, and it'd be very interesting to understand if there's some kind of cohomological or generalized cohomological definition in the generalized symmetry case. So I don't have an answer to that. So at best, what I'm going to do is rehash a little bit of old work, mainly work of Decopé, to tell you a little bit about this, and then I'm going to give you some examples of generalized symmetry fractionalization and generalized discrete torsion. Okay. Is that clear? Any questions?
So what happened to the obstruction to gauging in H4? Do you have?
Yeah, so the existence of this braided tensor functor kills that. That's equivalent to saying that there's no Toft anomaly. I should be careful here. I don't think I should actually include this beta here because in principle, I don't know, Corey can correct me if I'm wrong, but I think even if we have a non-trivial beta, in principle, we could still, as long as we're sort of gauging the two group, then the statement, you know, there would still be a braided tensor functor. So maybe you should, beta is, so if this is true, I could generalize this condition. I could allow beta to be non-vanishing. So maybe what you should really take seriously on this slide is the this Toft anomaly is vanishing. So I would love to have a cohomology to describe the general case, or maybe something smarter than cohomology. So if anyone has any ideas, please let me know. So let me just say a few things which are basically due mainly to Decopé and possibly to others. I certainly don't want to step on anyone's toes, but basically to understand gauging, what we can do is we can imagine starting from some space-time. So we start with some three manifold. Say, and I'm drawing it as some, just imagining that that's my three manifold, and I have in here some theory B1. Say, okay, so this is some unitary modular tensor category B1, and maybe it's two categorical completion mod B1 living everywhere. And now I'm going to imagine that on half of the space-time, essentially, maybe this half here, I'm essentially inserting this network of symmetry defects. In the group-like case, it was that sum on group-like symmetries. In the non-invertible case, it'll be a sum on non-invertible surfaces. And when I do that, I'm going to get at the interface. So here I'm going to have somehow inserted a sum over surfaces. I'm going to get an interface I, basically, between the theory that's the gauged theory and the ungauged theory. Okay. Maybe here, actually, in this diagram, I apologize, I've actually done it, the mirror image of this. So I've essentially done the gauging over here. Yeah. Yes.
Extremely naive.
No, please. Yeah.
I apologize for my ignorance. This is very general.
Yeah.
And very general fusion rules of whatever and symmetries. Are there any, even if hypothetical physical systems to which this potentially applies?
Yes. So in fact,
maybe
yeah.
this in the end, at the end.
I mean, I can say one thing briefly. I mean, so the answer to your question, I mean, an example that I'll actually discuss, people in the lab are essentially able to construct a system where you have hard code, let's say, on some lattice, and then a bubble, let's say, of quantum double of S3, which I'll get to in a little while. And then, you know, these surfaces here are exactly the kind of interfaces I'm talking about. And this is exactly a generalized symmetry gauging.
In a lower dimensional solid state.
This is a solid state device. This is two spatial dimensions. So it's of direct, whether we like it or not, this stuff is actually of direct relevant physical relevance, I think. Okay, so here we have here we have this right. So here we have this. Sorry. So yeah. Right. So essentially we've essentially gauged the symmetry corresponding to AS. So here I'm conflating. I apologize. As I said, I'm doing what I mentioned I might do, which is to conflate the fusion category with the object. And here I've essentially summed over AS on half the spacetime. And so what that means is that AS, these AS surfaces, they are essentially, of course, allowed to end on this interface I, right? Because I've constructed this part of the spacetime by summing over AS. So that should hopefully be intuitive. And in fact, by pinching now the interface, and this is used a lot in the second paper, which I described, but I'm not going to get time to discuss. This has some interesting quantum information implications, but you can pinch this surface I, and you can sort of then, you know, by pinching, you essentially get that AS turns into I dagger times I. And with a little bit more work, which I'm not going to get into, Decopé shows that really this AS surface is on the nose, essentially I dagger times I. And similarly, by pinching to the right, you can get sort of a dual algebra A hat S built from I corresponding to I times I dagger. So you can imagine doing the same trick here, but now pinching and getting a surface A hat S here. And in the case of the rep G, basically the rep G gauging, this is the surface basically. This would be some surface like SE. So imagine that we gauge some rep G in spacetime and we flatten it. The AS surface would be something like this SE surface, some generalization of it. And in fact, we can say a little bit more. So we can essentially, think about lines that live on this interface and we can sort of pinch them off. This will be familiar to people who've read the work of Kitaev and Kong. It's maybe some slight generalization of what Kitaev and Kong have done, mainly due again to Decopé and to others. But essentially what you can do is you can sort of take a line here, Y, that lives on this interface, and you can pinch it off and you get the boundary conditions living on AS. Okay, so you get the elements of this AS fusion category, and you can kind of go back and forth. And so that should make it kind of intuitive that by performing a folding, so if now we fold this theory, bring it over here, right? Then what we're going to get is we're going to get a gapped boundary, and living on that gapped boundary is going to be this AS fusion category, and the bulk that we're going to have is going to be essentially B1. Rather, I'm doing the folding the other way. We're going to get the bulk B1 times B2 bar. So we take Drinfeld center of the stuff that lives on the gapped boundary that we get by folding, by moving B2 onto the other side. We take the Drinfeld center of that, and we get B1 times B2 bar. And this is precisely the output from the braided tensor functor that I was describing at the end of in the last line of that table. So physically, that braided tensor functor essentially is going to give some B factor inside of this Drinfeld center. And I should also mention, I'm not going to have time to talk about it, but using that kind of logic and using these kinds of identities, you can prove all sorts of interesting things about Drinfeld centers of near group fusion categories. I know this is something that Terry has worked on, I think, and also Kawa Higashi and various other people who are here. You can prove some fun things, which we do in our paper. I won't talk about it because I don't have time, but so this should essentially motivate the output of that braided tensor functor, which is some Drinfeld center, where the original fusion category appears as a factor, basically. So this generalizes the Kitaev-Kong story, where basically this B2 bar would be the local, A modules of the algebra that they would condense. So let me say a few things now about generalized symmetry fractionalization. I know I'm running low on time, so let me just give you some examples of it. So generalized symmetry fractionalization, I want to think of as a choice of fusion rules given some fusion 1 category corresponding to surfaces. And at rank 2, famously due to Ostrich, there are 2 possible fusion categories, essentially. There's Z2. Well, there's also non-trivial associator, but there's basically Z2-like category and the Fibonacci category. And in our language, in the language of this generalized, symmetry fractionalization, I would think about these 2 choices, Z2 or Fib, as different examples of this fractionalization. So I don't know if you want to think of these as different classes of some kind of generalized homology. I'm not quite sure how to think about that, but something like that. From the fixed point theorem that I sort of alluded to, but didn't really have time to tell you, that the number of fixed points, the number of boundary lines is essentially given by the number of fixed points of the action on the bulk lines, we can conclude that the algebra, or at least the object, if I'm being a bit more careful, should be basically a sum of 2 surfaces. And in fact, in this case, they'll be trivial surfaces, where the first surface is bounded by the trivial line, and the second surface will be bounded by some non-trivial line. So in the case of Z2, it'll be the non-trivial element of Z2. In the case of Fib, it'll be the non-trivial element of Fib. And for Z2 fusion rules, now we can imagine different discrete torsions. So we get the usual discrete torsion, which corresponds in the Z2 case to the usual H3 classification. So we have Vec Z2 with some 3 cocycle. That could be trivial or non-trivial because this group is essentially Z2. These are the 2 Z2 SPTs in 2 + 1 dimensions. And gauging essentially the trivial case gives you the toric code theory. gauging the case with non-trivial associator gives you SU2 at level 1 Chern-Simons theory times SU2 at level -1, or if you like, what's called in the condensed matter world, the double semyon. And in both cases, you have the same fusion rules, but the associator and the modular data differ because basically you've stacked with different SPTs. Okay. On the other hand, in the case of Fibonacci, again, due to Ostrich, there's a unique choice of F. So there's no SPT basically in this Fibonacci case. So whatever cohomology comes up with should yield for Fib something trivial. So what we need to do is work a little bit harder to find examples of generalized SPTs. I see I'm running very low on time, so I'm not going to go through the nitty-gritty details, but just to say, if you want, you can see the examples, some examples of this in our paper. And the basic idea is to take S3 discrete gauge theory, which is think of here, slab experiment, and you can have different twists. So there are 6 possible twists because this H3 S3 U1 has 6 non-trivial, six different elements. And basically, I'll just sort of give you the upshot. I'm not going to go through all the details here, but basically what you can show is you can take the 6 different twisted S3 discrete gauge theories, and you can show that basically they all come from gauging either toric code with algebra object S1 plus SE, where SE is this non-vertical surface, or you can show so half of them come in that way. The other half come from essentially taking double semyon, which is this Z2 discrete gauge theory with non-trivial Dycroft-Witten action. And so this will give some of the twists. So the toric code will give the even twists, if that means anything. And the double semyon gauging will give you the odd twists. Sorry, 1, 3, 5. And the odd twists are these are just the different examples of generalized SPT in this case. Basically, you have 6 different examples of generalized SPT. This is a non-invertible symmetry, so this is not the usual. This is not classified by the usual H3, but this is a concrete example. Okay. So, right, I was going to give you some more details about it, but I think I'm running low on time, so I'll skip those details. That's essentially the summary, the same. So this is the thing that you gauge, this case here, yeah, so that's essentially the summary. So let me just get to the conclusions. So there's an interesting and rich generalization of G-equivariantization. It would be nice, at least from my perspective, to have some kind of more unified, maybe understanding or cohomological understanding, because maybe that leads to a better way to think about anomalies in these non-invertible cases, because anomalies ought to be classified by something rigid, right? Something maybe related to cohomology. So I would love to have sort of a nice cohomological generalization of the invertible case. Also, it'd be interesting to apply this stuff to fermionic theories, and of course, generalizations to non-topological quantum field theories. So these are all sort of things on the to-do list. So thank you.